Hello everyone, welcome to lecture 26 in physical organic chemistry, in which we will continue our discussion on pericyclic reactions. In our previous class we had seen the 1,3 dipolar cycloadditions, and in today's class we shall see the sigmatropic shifts, the theory and applications. As always, most of the lecture material in the topic of pericyclic reactions has been sourced from Professor Shankaraman's uh, textbook on pericyclic reactions as well as his lecture notes. Coming to sigmatropic rearrangements, essentially sigmatropic rearrangements are the reactions that involve the breaking of a sigma bond and migration of a group over a pi electron system, leading to the formation of a new sigma bond at the terminus of the pi system, along with the reorganization of the pi system. Everything in a concerted manner in one particular step. How do you classify sigmatropic rearrangements? The order of sigmatropic rearrangements is indicated by two numbers in a square bracket: 1, 3, 3, 3, 1, 5, etc. The numbering starts from the sigma bond that is broken and is counted through the pi framework to the terminus where the new sigma bond is formed. In any rearrangement, we know that if there is a system of this kind and we have a migrating group X which goes on to then form this kind of a system, then this is the migration origin and this is the migration terminus. The same thing applies to sigmatropic rearrangements. How do we start counting? This is the bond that is being broken. So you start numbering the carbons or the elements accordingly as 1, and then you go over the pi framework in this particular fashion. So you can see here the bond that is breaking is 1, 1. The bond that is going to result is between 1 and 3. Therefore, this shift is a 1,3R shift. Similarly, in the next example, you can see this is a 1,5 shift because the new sigma bond is going to form between the 1 position here and the 5 position here. In the next example, you can see it is a 3,3 sigmatropic shift. So you start numbering from the sigma bond that is being broken. So 1, 2, 3, 1, 2, 3 going over the pi system, and the bond that is going to form is between the 3, 3 position. Therefore, this is a 3,3 sigmatropic shift. Similarly, you can have 2,3 sigmatropic rearrangements. You can also have 5,5 sigmatropic rearrangements. This is the very famous benzidine rearrangement. So what about the stereochemistry of sigmatropic rearrangements? As in the case of cycloaddition reactions, stereochemical possibilities also exist in sigmatropic rearrangements. In the case of hydrogen migration, obviously, it can migrate from the terminus it can migrate to the terminus from the same phase of the pi framework to which it was originally connected, or it can migrate to the opposite phase of the pi framework. In the first case, that would correspond to a suprafacial shift, whereas in the second case, it would correspond to an antefacial shift, with respect to the pi framework. Obviously, it will give you opposite stereochemistry at the newly formed sp3 center. What do we mean by this? You look at the first reaction, this one. So in this particular case, this is migrating from the same face of the pi system, whereas in this case, this is migrating from the opposite face of the pi system. So in the first case, it is a suprafacial shift, whereas in the second case, it is an anterofacial shift. Something like this. The group is moving across the same face. And in the anterofacial migration, the group is moving from one face to the other. This was about the H migration. What about carbon migration? In the case of migration of a carbon center, we need to specify the mode of migration of that carbon center with respect to itself and with respect to the pi system. What do we mean by this? The migration can take place in an all suprafacial or an all anterofacial manner with respect to both the sigma system and the pi system. Or it can be suprafacial with respect to one and anterofacial with respect to the other. So when a carbon center undergoes an anterofacial shift, the configuration at the center is inverted necessarily because it is something like a backside attack similar to the SN2 reaction. We'll see what this means. Now, although you can have 4 modes available that are listed here, very often the symmetry as well as the geometry as well as steric factors will limit the migration of the sigma bond to one particular mode. Okay, so it's not necessary that all 4 modes will be possible. Okay, so we will have some symmetry rules, there will be some geometric implications, there will be stereo electronic factors involved. All these will impose certain barriers on certain pathways and will limit the migration of the sigma bond to one particular mode. Particularly the antra-antra mode that you can see here is one of the least preferred modes because the reacting ends have to reach each other from the backside. So let us first look at the suprafacial migration, this one. So what's happening here is with respect to this particular system, it is suprafacial. With respect to this pi system, it is suprafacial. Therefore, this in the first case, you will have retention at this particular carbon. In the second case, the pi system is suprafacial, but the sigma system now reacts from the back. That means the lobe at the back, that is of this sigma bond, is now going to react similar to an SN2 reaction, obviously leading to inversion at this particular center. So you can see here now this center is inverted with respect to the starting material. Same is true for the supra antera. So with respect to the pi system, this is antera, and with respect to the sigma system, this is supra. Whereas in the other case, it is antera with respect to the pi system and antera with respect to the sigma system, again leading to inversion. Now, how do you analyze the sigmatropic rearrangements about the permissibility of the transformation? So, except for the NN, for example, the 3-3 sigmatropic rearrangements or the 5-5 sigmatropic rearrangements, the others do not possess any symmetry element. The transition state for some of the sigmatropic rearrangements may possess elements of symmetry, but not the starting material or the product. Okay, so only the transition state of some of the sigmatropic rearrangements may possess some elements of symmetry. Therefore, what does this mean? This means that the use of orbital symmetry correlation method for analysis is not relevant for sigmatropic rearrangements. Then what analysis should we use? The frontier orbital method and the transition state aromaticity method are useful for the analysis of sigmatropic rearrangements. And on basis of this, we can arrive at the Woodward Hoffmann rules. So now there are several variations of the frontier molecular orbital method for the analysis of sigmatropic rearrangements. And they will all come to the same conclusions in terms of the Woodward Hoffmann rules and the prediction of the stereospecificity of these reactions, whether this will be antera or supra. Now, how did Woodward and Hoffmann do the arrive at the rules for sigmatropic rearrangements? What they did is that they considered the dissection of the transition state of the sigmatropic rearrangement into two formal radical fragments, one corresponding to a carbon-centered radical and other to a non-bonding orbital of a conjugated radical containing odd carbon atoms. Thus, the transition state for a 1,3 migration, for example, might be considered as a combination of a carbon radical with an allyl radical. And a 1,5 migration, for example, can be considered as a combination of a carbon radical, that is 1, with a pentadienyl radical, that is 5. So for a thermal 1,3 migration, the supra-supra shift will be forbidden. Why? Because it leads to an antibonding interaction of the migrating group. For example, let us look at this particular diagram. Let's first look at the 1,3H shift. Then we will see the 1,3 carbon shift. So you can see here the supra-supra. For in case of hydrogen, there is no supra-supra. Sorry. So it's only a suprafacial. So the suprafacial 1,3H shift is forbidden because now you are having an antibonding interaction, whereas the antrafacial 1,3H shift is allowed. But we will see why this is not very feasible in the coming up slides. If you see the 1,3 carbon shift, the suprafacial is forbidden with respect to the pi system. Why is this forbidden? Again, we are seeing here an antibonding overlap. Whereas for the antrafacial shift, obviously, if this is going to be the antrafacial shift, then it is going to be a suprafacial with respect to the pi system, but antrafacial with respect to the sigma system. You can see here now there is a bonding overlap in the transition state, and therefore this is allowed. And obviously, since this is antrafacial, there is inversion taking place. So we can see here, if this particular substrate is taken, then no such transformation is observed. Why? Because first case, suprafacial 1,3H shift is forbidden. The antrafacial 1,3H shift is allowed, but the bridging distance is too great for the antrafacial migration. Geometrically, this is not allowed. Therefore, you can see here the H or the D shift, 1,3 shift does not occur thermally. Okay. What about carbon shift? The carbon shifts do take place, and these rearrangements are seen only in systems that are highly strained. Okay. Only in highly strained systems we can see. Why we can see such shifts? And again they have to be antifacial, because these are highly strained and very close to each other. Also, this strain lowers the activation for the rearrangement. What about the thermal 1,5 shift? The thermal 1,5 shift is symmetry allowed in a supra-supra mode, whereas in the supra antifacial mode it is forbidden. Again, why? Because of the overlaps in the transition state. So you can see here in the supra-supra you are seeing bonding overlaps, whereas in the supra-antra you are seeing an anti-bonding overlap. Once again, by the frontier orbital method, you can see here these are the electrons that belong to this particular portion, the sigma portion, and in the photochemical method this will be your orbital diagram. So we can view this as an R radical and a cyclopentadienyl radical. Okay, so you can see here in this particular case the suprafacial overlap is preferred in the transition state, as you can see in this particular diagram, and the antifacial, which will lead to inversion, is disfavored. So in a 1,5 shift, the supra-supra is favored, leads to retention, whereas the supra-antra leads to inversion, and this is thermally disfavored. What about the Dewar-Zimmermann analysis via aromaticity of transition state? Let us see what this method predicts. This method, let us come to the 1,3 shift for hydrogen. What we are seeing here, we are seeing two-phase inversions. Therefore, how many electrons are involved? There are 4 electrons involved. There are 2 pi electrons and 2 sigma electrons. And we can see here, this is a Huckel type topology because there are 2 phase inversions. It is even number and there are 4 electrons. Therefore, this is thermally forbidden. What about the 1,5H shift for a hydrogen? We have 6 electrons here and we can see here there are 0 phase inversions and that's an even number. This is a Huckel type of topology and there are 4n plus 2, 6 electrons. Therefore, this is allowed thermally. Same way, the 1,5 alkyl shift or C shift is again having 0 phase inversions. Obviously is a Huckel type topology. 6 electrons are involved. 4 from the pi system, 2 from the sigma system. Therefore, this is allowed thermally. What about the generalized orbital symmetry rules? Let us see for a 1,3H shift. So we are seeing here a 1,3 antra shift for the hydrogen. It is orbitally allowed but geometrically not allowed. It is disfavored because the small size of hydrogen does not allow the overlap. So let us see how many 4R antra components do we have? We have 0 components. How many 4Q plus 2 supra components do we have? We have 1 component, which is this one where Q is 0. Therefore, the total is odd. Therefore, this is thermally allowed. So the antifacial shift is orbitally allowed for the H. What about the antifacial shift for the alkyl? So you can see here It is supra with respect to the pi system and antra with respect to the sigma system. So you can see here this is an antara attack for the sigma system. So here one orbital is interacting, here the second orbital is interacting. These are antara, an SN2 type of attack. So you can see here in the transition state, how many antra, 4R antra components do we have? We do not have any of them, so 0. How many supra components do we have? We have the pi to s supra component, which is 1. Therefore, this is thermally allowed. What about the generalized orbital symmetry rules for 1,5 shift? In the 1,5 shift, we can see here this is a supra-supra overlap. So in this particular case, it is geometrically allowed, symmetry allowed. Why? Because the 4 are antra components. We don't have any antra components, so it is 0. How many 4q plus 2 supra components do we have in this particular case? We have 1 4q plus 2 supra components where q is 0. Therefore, we have 1. The total is odd. Therefore, this is thermally allowed. So, the pi 4s plus sigma 2s is thermally allowed. Since this is supra, this will lead to retention of stereochemistry. So let's generalize the Woodward Hoffmann rules for the 1n hydrogen shift. As we have seen, for the 1,3, the allowed is pi s plus sigma antra, or the pi antra plus sigma supra under thermal conditions. It is forbidden under photochemical conditions. Whereas for the 4n systems, the supra-supra is forbidden. For a 1,5 type of shift, we saw the supra-supra for the hydrogen also is allowed, whereas for the supra-antra or antra-supra, it is forbidden. What about the alkyl shifts? For alkyl shifts, we can see here the 4n systems we just saw, 1,3 type of rearrangement. It is allowed when it is pi supra and sigma antra. Obviously, because it is sigma antra, it will be allowed with inversion. In the photochemical case, this is forbidden. It is also allowed with the pi antra and sigma supra. Again, this is allowed with retention. This is a difficult case. The supra-supra we saw is a forbidden case for 4n system. What about 4n plus 2? The 4n plus 2 we just saw a 1,5 shift where the pi supra plus sigma supra was allowed with retention under thermal conditions. For the other systems, the supra-antra or the antra-supra, it was forbidden. Whereas the same was then allowed with inversion or retention depending on what happens at the sigma system under photochemical conditions. Let's see now a couple of 1,3 sigmatropic shifts for the hydrogen atom. Now this is symmetry allowed process in the antrafacial mode. In the concerted process, obviously the transition state would involve the overlap of the 1s orbital of the hydrogen simultaneously at the 1,3 positions of the framework. Now, in the antrafacial shift, this is geometrically not feasible. Therefore, the 1,3 sigmatropic shift of hydrogen atom is extremely rare. An example of this is given in this particular example. Look at this. This is the tautomer of toluene. Now this is highly stable. Surprisingly, it does not convert into toluene. Why? Because this is symmetry forbidden in the suprafacial mode and geometry forbidden in the antifacial mode. This particular compound is thermally stable in gas phase up to 350 degrees. In fact, it is actually prepared at such high temperature by the pyrolysis of this particular carbonate. And in solution also, this is fairly stable and undergoes a very facile Diels-Alder reaction with tetracyanoethylene to give you this cycloadduct. This clearly shows us that the 1,3H shift is not feasible in thermal condition. What about photochemical condition? In photochemical condition, the 1,3 sigmatropic migration of hydrogen has been well reported from the singlet excited state. For example, you consider this particular example for the exocyclic olefin. Now, if you replace this with deuterium, you can very easily see that this H will now end up at this particular position. So it will be a 1,3 migration, and you can see very clearly if this is now substituted with deuterium, the kinetic isotope effect of 2.8 is observed for the migration, which clearly indicates that this is an intramolecular H shift and it is in a 1,3 fashion. Obviously, this is happening only under the photochemical conditions. What about alkyl shifts? The Woodward Hoffmann rules predict the photochemical 1,3 sigmatropic C shifts to occur in a suprafacial mode with retention of stereochemistry at the migrating center. As you can see here in this particular example, under photochemical conditions, this particular skeleton rearranges with the retention of stereochemistry at the migrating carbon center. What about antifacial 1,3 sigmatropic migrations? Obviously, these have to be allowed under thermal conditions only, and since this is antifacial, it will lead to the inversion of configuration. For example, let us consider this particular reaction. This is now undergoing a 1,3 sigmatropic shift of the carbon. Obviously, it has in an antifacial mode leads to inversion. Now, this particular system was deliberately designed because it can undergo only a suprafacial, pi suprafacial, sigma antifacial shift, because the other alternative, which is also possible thermally, is an pi antifacial and sigma suprafacial shift. But that does not happen in this particular case because it would lead to a highly strained bridged system, which is geometrically not feasible in the 2-to-1 ring system. This is the 2-to-1 ring system. Okay, so that is not feasible. So this clearly tells us that this migration is a 1,3 sigmatropic migration in the antifacial mode with respect to the sigma system. Okay, like we had mentioned earlier, these type of shifts will occur only in systems which are highly strained. For example, let us look at this particular thermolysis. Now you can see here in the starting material, in this particular example, the deuterium and the acetoxy are on the opposite side. Whereas after the reaction has taken place at 300 degrees, the deuterium and acetoxy are now exo and they are syn with respect to each other, or cis with respect to each other. Obviously, there has been an inversion at this particular center. So you can see here, this is the transition state for the antifacial shift, and this is thermal and it is 1,3 shift. Obviously there has to be an inversion at this particular center. Therefore now these two are cis with respect to each other. In the other example, in the starting material, the deuterium and acetoxy are cis with respect to each other. In the product, the acetoxy is exo, but the deuterium is now endo. The selectivity is more or less the same in both the cases, clearly indicating that there is an antifacial shift with respect to the sigma system. Same here, you can see here the acetoxy and the methyl, again they are cis with respect to each other in the product. In this case also, the stereochemistry at the migrating center has been inverted. Another example, let us see here. In this particular case, there is a very high selectivity for this particular reaction. So you can see here, the symmetry controlled product is obtained in a very high ratio with respect to the other product, which is not symmetry controlled. Not only that, it was observed that if this carbonyl is not there in the starting material, then the reaction occurs 10 raised to 5 times slower, which indicates that there is a conjugation of the carbonyl pi orbital with the orbital of the migrating center in the transition state, which leads to a greater stabilization of the transition state. In the next reaction, it is a thermal rearrangement of this exomethylene cyclopropane. Again, it occurs with inversion at the migrating center. So, either of the groups can migrate, either this one or this one. Depending on which of them migrates to this particular terminus, you will get either this product or this product, and you can see that the relative stereochemistry is maintained or has been inverted at the migrating center. Okay. Now this is an example in reaction A. You can see here, this is an example of a walk rearrangement. Okay, so the alkyl group is actually walking across the system. What is important to note is that the relative stereochemistry, okay, the exoester remains exo in the product throughout the rearrangement. You see here, this can keep walking. Okay, you can keep getting 1,3 shifts. Either of these, first you can get the migration of this particular bond, then later on you can get the migration of this particular bond. Similarly, you can get the migration of this particular bond to this particular terminus. All of these are 1,3 shifts, and in each case there is an inversion of stereochemistry with respect to the migrating center because it is an antifacial migration, which indicates that the CO2 Me group will always remain exo with respect to the bicyclic system. If this was not an antifacial rearrangement, then the suprafacial shift of the carbon would mean that the exo and endo groups would exchange their positions for each migration, thereby losing the stereochemical integrity, which does not happen. So this is a classical example, a kind of a proof for the antifacial migration for the 1,3 shift. In the second example, this is a chiral starting material which racemizes at this particular temperature. So you can see both of these are images, mirror images of each other. Why does this happen? Because the rearrangement, as you can see here, leads to the other enantiomer of the starting material, thereby racemizing the starting material thermally. And since this has to now take place antifacially, there has to be a inversion in the stereochemistry. Therefore, what happens? You end up getting racemization of the starting material. In the next example, that is example C, there is a thermal isomerization of this starting material, which proceeds via the formation of a vinyl cyclopropene. So you can see here in the starting material, you have two deuteriums here. These end up into the 5-membered ring system. So there is a kind of a ring expansion taking place via an alkyl shift in a 1,3 fashion, proceeding in an antifacial manner. In our next class, we will continue our discussion on sigmatropic rearrangements. We'll also see the theory behind a variety of other rearrangements, and we'll see the applications of these rearrangements. Thank you, everybody. We'll see you at the class tomorrow. Goodbye.